All right, now am I able to call BART at this moment? No, we're not connected yet. So it says we're connected. So can I share the screen? Okay.
Hacker did.
That'd be frustrating. We have to do one long, Yeah, test. Maybe. Hopefully. Bart may have left us. Well, hopefully this still works. All right, we'll go ahead and get started. Part 2, actually your second project, which is in Lab 2. Well, I really need to update my slides, don't I?
Lab project, not so big a deal.
Yeah, Lab. Really, this PDF is just telling you to go look inside your p2.txt file for more details and to give you a little more hints about how to use GitHub, since we've had a couple of people have issues. Please do email me or come talk to me if you need more help with GitHub. It's going to be due on March 16th, which I believe is right after spring break. Yeah, right after spring break is what that ends up being. So fair warning, I highly recommend that if you want to have a break during spring, to get it done 2 weeks before then, or a week before then, so you don't have to work over spring break. You have been warned. Let's go look at it. All right, so assignment 2. Yeah, it says March 13th. There.
Yeah, that's the one I read. I was like, I thought it was the 13th, but I
Oh,
didn't say anything.
I think I misspelled February. Anyways, the first one was an in order CPU. This one's going to be out of order. It's essentially the same thing as assignment 1, except now I'm asking you to implement the Tomasulu method for the out of order processor. So you will write a cycle accurate simulator for a pipeline implementation of LC that performs dynamic instruction scheduling, aka the Tomasulu method. So LC is very simple, 8 registers, 32-bit. I've already talked about this last time, so I put it back in here just in case you need to see the format again. But let's go ahead and jump down to section 3. It does require you to a construction of a pipeline simulator, written in C or C++. If you really want a different language, please email me. But I think so far people are sticking with that, except for one exception. Someone's doing C#, which should be okay. Solution should be the source code, and any test programs verified. Keep that in mind. I am looking at your test cases to make sure it does work correctly. Failure to provide the write-up or failure to provide a complete set suite, aka test suite, will result in a lower grade even if the simulator correctly passes all of my test programs. We're going to use a data path similar to the Pentium to Pro discussed in class. We're going to discuss this right after this project, or this lab. Actually, I should probably stop now and do the whole Pentium Pro, so this makes more sense, because now when I'm going into fetch, these parts aren't going to make too much sense. So let me go ahead and move this to the background, and let's go ahead and look at the PowerPoint, which I dropped inside of your O2 out of order simulator directory, so you can go ahead and review it.
Without having to go outside of the folder.
I know. You're welcome. Make sure there's no other points. Okay. So out of order execution with the Pentium Pro. Also, this continued in the Pentium 2, 3. Really, it continued to 4, and basically up to date. The structures that are being used here are still utilized nowadays. Okay. Before we go into it, a little background story with x86, because it can be a little confusing trying to merge the little computer instruction set and the x86 instruction set. The IA32, which aka x86, namely what Intel and AMD chips are a very complex instruction set. For example, an instruction has varying length between 1 and 17 bytes. It can have a prefix, up to 4 prefixes, 1 byte each, or none at all. So 0 to 4 bytes right there. followed by a 1 or 2 byte opcode, followed by a MARD RM, which is 1 byte only if the instruction requires it. I forgot what SIB stood for, but it was another 1 byte only if it's required. The displacement, depending on your architecture, if you're doing 8-bit, 16-bit, 32-bit, will be 1, 2, or 4 bytes. And then the immediate field, again, can be 1, 2, or 4 bytes, depending on what the instruction is. So Matt, do you want to write a decoder for this?
No.
No. This is why we're sticking with LC. Do keep in mind that the IA32, this isn't even 64-bit, this is just standard IA32, is pretty complex. The issue was that when you want to take these instructions and actually migrate them into something that can be used, no sound again. Wow. I'll see if I can give that to you. I'm screen sharing. Is it on now?
Blah.
Thanks, Matt. Sounds like a no-go to me. All right. We'll try. Nope. That isn't gonna be fun. How about this one? Test, test, test. I'll go ahead and see if I can load up a. Ooh. So recording. Oh, it's not even coming up for you. Yeah, you don't exist, apparently.
Ouch.
Huh. Hmm. I don't know how to. I think we have to talk to Bart about this because it's not going to work. Because it looks like we only have the option between. Yeah. All right, I'll have to talk to Bart about that. Okay. But at least we have a video recording. Break up instructions into RISC-like micro-operations. So what's happening is, you know, LC Computer had very small instructions, or very simple ones. Yes?
Mm-hmm.
So what Intel did is they just took our very complex instruction set and then would spit out the micro ops for them, and then the compiler or the processor would take it from there. So you literally had a piece of hardware in the beginning that took these complex instructions and broke them up either into 1, 2, 4, and in some cases 16 or 18 different instructions.
Gross.
Yep, decode is gross, but simplifies execute greatly and turned out to be a far better solution. Okay. So first stage, okay, so what's going on Pentium Pro with the process? The first stage consists of just fetch, decode, and convert into micro ops, and then we have register renaming with the Tomasulo method. What has been added is there's a reorder buffer. It's the buffer between the first and second stages, and also it's between the second and third stages, which is to help ensure that instructions are committed at the right time. The third stage requires the micro operations in the original program order, so completed micro ops wait in the reorder buffer until all the preceding instructions have been retired. So this is going to be a method that you send it out in the wild of the out of order processor, and then when it's done, you're going to have a reorder buffer to make sure that things are committed correctly. It's going to look something along this. This is the Pentium 3 architecture. All right, Matt, what looks familiar?
You got your fetch and decode.
Okay.
You got an instruction cache. Register file.
Mm-hmm.
That floating point unit there.
That floating point unit there.
Yeah, it looks like some of their acronyms are different too.
So it's very similar You still have your instruction cache. Notice you have a huge decoder, but it's going to turn it. It talks to a ROM to take the complex instruction, turn them into simple RISC-like instructions, like with the LC computer, little computer. And then here's your reservation station, 20 entries. I can then go to different units, data store, address, as well as floating point and integers. And I just realized what I can do to help Bart out, so I'm going to stop the recording right now.